Hey guys, and welcome to another A-Level 4 Maths revision video. Today we're taking a look at a core pure topic, which is proof by induction. So this is quite an important topic, especially in, if you're going to take maths on at university. We can prove a lot of things using proof by induction. So a very important skill. And in this topic today, we're only taking a look at the book 1 material. So proof by induction is mainly just an AS topic, but obviously if you're doing the A level as well, you need to know the AS. So let's jump straight into this. Let's have a look what we've got. So this first question here is one of these identify the error questions. So these questions, you've not really kind of come across them before. The best way to tackle them is to just kind of work through yourself and see if you can identify on what line the error is. So question 6. So if we imagine we're starting this ourselves. So for any proof by induction question, we start with the base case, so we're letting n equal 1. So they show that the left hand side is 1 squared, which is 1. Okay, so that's not a problem. The right hand side is just the sum of 1 squared here, basically, so that's just 1 as well. So the left hand side is equal to the right hand side. So far, that's perfect. The next step here is they assume the statement is true for n equals k, and they actually demonstrate that. Okay, so again, at this point, there's nothing wrong. So we go on to the final step of a proof by induction here, where we normally let n equal k plus 1, and they do here, but you have to show yourself why this is true for n equals k plus 1. You can't just assume it, which is essentially what's been done here. So what we'd say is, for part A, the student hasn't shown why this is true. Okay. It's true for n equals k plus 1. So you can't just quite, plug in n equals k plus 1 and just assume it's true. You have to show why. So that'd be the error there. And then part B asks us to just give a counter example to show that it wasn't true anyway. So there's multiple different answers you can give for this. So for example, if I let n equal 2, so for a question like this, just play around with a few different numbers, see which ones work and don't. So if I let n equal 2, for example, well then the left hand side, what would that give us? Well, that's going to give us the summation from r equals 1 to 2 of r squared. Okay, well what would that give us? So that's 1 plus 2 and then square it, so that's 3 squared. The right hand side, what would I get from this? So this is the summation of 1 squared plus 2 squared. So summation from r equals 1 to 2 of 1 squared plus 2 squared here. Well, what would that give us? So that's going to be 1 plus 4, so that's 5. Well, 9 is clearly not equal to 5, for example. So n equals 2 is just a really easy example you could give. If you let n equal 3 again, there's another example. This would not work either. So your left hand side would be 36. That's 36. The right hand side, that would give you 14, and quite clearly 36 is obviously equal to 14, right? So like I said, there's a lot of different examples you can give there. Any one example is absolutely fine. So yeah, so a nice easy question to get us started. Let's actually jump into doing some proof by inductions ourselves. So this is a divisibility result. So what we're looking to show here is that 8 to the power of n minus 3 to the power of n is divisible by 5 for any positive integer. So the first thing we do is we start with the base case. So we let n equal 1. Okay. Well, if n equals 1, that's 8 to the power of 1 minus 3 to the power of 1. Which is just 8 minus 3, which is equal to 5, and obviously 5 is divisible by 5. Okay, so therefore it's true for n equals 1 as 5 is divisible by 5. Okay. Now we assume it's true for n equals k. Okay, so assume true for n equals k. And with this step here, we want to kind of demonstrate what's happening. So if n is equal to k, what we actually have is 8 to the k minus 3 to the k is equal to, well, it's divisible by 5. What you should understand here is that it's a multiple of 5 in essence, because if I just let it be equal to 5, again, it doesn't really matter. If I just say it's 5p, but we've got to just make a little clarification here. P has to be a positive integer. So basically, where p belongs to the positive integers. Okay. So what we're saying here is that 8 to the power of k minus 3 to the power of k is divisible by 5. You know, you can write it as 5 times something. Okay, so it's in the 5 times table. It is divisible by 5. And then we're going to use this expression here to show that it's also true for n equals k plus 1. So let n equal k plus 1. Well, if n is equal to k plus 1, what we've got here is 8 to the k plus 1 minus 3 to the k plus 1. And again here, if this is true, this is divisible by 5, it will be equal to 5 times something. So this time I'm going to write it as 5q. And again, q must be a positive integer. Okay, so q is a positive integer, just like p. So this is where you've just kind of got to think about what's the easiest way to kind of get this in the right form. The first thing that's, well, I'm going to say it's often the case, it's usually always the case with these questions. We need to manipulate the exponents here, so the powers. Well, I can write that as 8 to the 1 times 8 to the k, right? So that's 8 times 8 to the k minus, again here, this is 3 to the k times 3 to the 1. So that's 3 times 3 to the k. Now, there's a few different ways you can show this result. Usually for Edexcel, in the mark schemes, they use the k plus 1 notation, and they'll subtract like a multiple of fk. That method's absolutely fine. I prefer to kind of do it like this, but again, it doesn't matter which way you do it, as long as you can show at the very end that it's divisible by 5. So what I'm going to do here, obviously I'm going to make use of the fact that 8 is equal to, well, basically 5 plus 3, for example, right? We can use that result. So I can rewrite this now. So manipulating this is equal now to 8 lots of 8 to the k minus 3 to the k. But if you notice, if I was to expand this would give me that part there, that's fine. But this would give me basically minus 8 lots of 3 to the k. We don't want minus 8 lots, we have minus 3 lots. So what do I have to add to this to get this? Well, I need to add 5 lots. Okay, 5 lots here of 3 to the k. Actually, in fact, it's alright as a bracket like that. 5 lots of 3 to the k. Well, the important thing to notice here is that we have 8 to the power of k minus 3 to the power of k. We already know this is divisible by 5 because we assumed it's true for n equals k. And we've shown that this is equal to 5 lots of a positive integer, so it has to be divisible by 5. So this part here is just 8 times a number that's divisible by 5. So this part's always divisible by 5, so this is divisible by 5. Divisible by 5. This part here is 5 times a number, so it doesn't matter what this number actually works out to be, because it's times by 5, it will always be divisible by 5. So this is also divisible by 5. And, well, the summation here, so you've got a number that's divisible by 5 plus another number that's divisible by 5, the result will also be divisible by 5. So what we can actually say here is that f of n will be divisible by 5. So therefore, f of n will be divisible by 5. Divisible by 5. Because the result here, so this is divisible by 5. This is also, because it's 5 times it. So they're both divisible by 5. If you have two things that are divisible by 5, the result will also be divisible by 5 as well. So at this stage here now, you have to give kind of the conclusion of a proof by induction. You will lose marks if you don't include it. It's really tedious. I'll see if I can fit it all in. So we've said fn will be divisible by 5. Fn will be divisible by 5 when n equals k plus 1. That's what we've just proved. So when n equals k plus 1. So if f of n is then divisible by 5, then we've also shown that fn is divisible by 5 as well. So this implies f of n, or 5 divides f of n. So what's the next part? So if fn is divisible by 5 when n equals k, so that's when n equals k, sorry. So it helps if I lay it out, well, this is not well at all. Then this also implies 5 divides f of n. And then, well, basically, as f of n is also divisible, or if f of n is divisible by 5, when n equals 1, n equals 1, then f of n is also divisible by 5. Or 5 divides f of n. And at this stage here, this shows that it's true for all, for all n equals 1, n equals greater than or equal to 1, and then for all positive integers, and then for all n that belong to the positive integers. So I'm running out of room here at the bottom, but hopefully you can just about make that out. I might have to leave it in the description, that's a bit messy, but hopefully you can kind of understand what I'm saying there. And then that gives us the result there. So we've proven that 8 to the n minus 3 to the n is divisible by 5. Right, so let's move on to the matrices now. So proving by induction for matrices. So I actually quite prefer these ones. Usually students don't quite like them at first, but once you kind of get your head around it, definitely nice and easy. The first thing we always do with any proof by induction is let n equal 1. So let n equal 1. Well, if n equals 1, what I get here is 2, 0, 1, 1 to the power of 1, which is just that matrix itself. This should be equal now to wherever I place n here by 1, we should get the same thing. So 2 to the 1, well, that's just 2. 0, 2 to the 1 minus 1, we should get 1, which we do. And then 1 is quite clearly equal to 1. So at each stage here, each part of the matrix, we get the same. So therefore, it's true for n equals 1. Left hand side is equal to right hand side. Okay, so we've shown left hand side is equal to the right hand side, so it has to be true for n equals 1. Next step, like always, we assume it's true for n equals k. I'm not sure why I'm writing it out fully. So assume true, n equals k. So if it is true for n equals k, what we're saying then is 2, 0, 1, 1 to the power of k is going to be equal to this. So again, wherever you see an n on this right hand matrix, replace it with a k. So 2 to the k, 2 to the k minus 1, 0 and 1. Okay. So finally, what we do is we let n equal k plus 1. And now we write our matrix back out. So how we have it. So this is 2, 0, 1, 1 to the power of k plus 1. Well, this would just be, again, splitting up your powers here. So these proof by induction, like you see, you just got to be aware of this fact with your powers. This is 2, 0, 1, 1 to the power of k times this matrix again to the power of 1. Like so. That'd give you the same result here. Now, this matrix here to the power of 1, we know quite clearly that that's just 2, 0, 1, 1. But here, this 2, 0, 1, 1 to the power of k, we know this is what it's equal to. So we can rewrite this as 2 to the k, 0, 2 to the k minus 1, and then 1, times by this matrix here. And at this stage here now, we just need to actually multiply out here. So just make sure you're confident with multiplying matrices. It's only a 2 by 2 matrix, so it shouldn't be too complex. So if I expand this row here with this column, so 2 times 2 to the k, so 2 times 2 to the k. what I'll do is I'll write everything out in full and then we'll simplify it once more. This row by this column, well, 2 to the k times 0 is 0. 0 times 1 is 0, so that's just 0. 2 to the k minus 1 times 2. So that's 2 lots of 2 to the k minus 1. And then we also have 1 times 1. Okay, so that's plus 1 there. Hopefully I don't run out of room. And then finally, this row here times this column, so that's 0. And then 1 times 1 is just 1 there. Okay, at this stage here, we just need to simplify this. Now, before we actually simplify this, what we should expect is if you take this right-hand matrix here, so this one here, and you sub n equals k plus 1, that's what we should get. So what we should get here is 2 to the k plus 1, 0, 2 to the k plus 1, minus 1, and then 1. Okay, we essentially know whether we've got the question right or wrong. If we don't get that, I've done something wrong previously, but I don't see anything wrong with it, so it should work out. This is 2 to the 1, so times in these you add the powers, which gives us our top left element perfect, 2 to the k plus 1. The right hand element here, top right, is 0. This would be 2 to the k plus 1, minus 2, and then add the 1. So I give you the minus 1 there. Perfect, that works. So that's 2 to the k plus 1. And then that'd be 2 times minus 1, which is minus 2, add the 1. Gives you the minus 1. And then finally, just the 1 in the bottom right. Perfect. We got exactly what we needed, okay? So, the proof is actually just complete there. We've shown exactly what we needed to get. Now again, to finish it off, we just need to write basically all the nonsense, the waffle. So, if we do that, so therefore, the matrix is true for n equals k. Well, what I should say is if the matrix is true for n equals k, then it's shown to be true for, so be true for n equals k plus 1. So as the matrix equation is true for n equals 1, so as the matrix equation is true for n equals 1, this implies that it's true for all n that belong to the positive integers. And there we have it. So I'm kind of writing this shorthand. If you've not come across this notation before, this just means for all n that belong to the positive integers. So you should be okay with this notation, but just in case you've not seen this before, that's for all n there. And there we have it. So just one more question now. Again, just another matrix one, but just practicing it. So this is from review exercise 2, question 5. Same kind of idea again. We've got a matrix A, and we want to prove by induction that for all positive integers m, a to the n is equal to this matrix here. So it's not actually kind of shown, but it's basically just the same as the last one. So imagine you take this matrix A here to the power of n, we get this. So that's 3, 1, minus 4, minus 1. The power of n is equal to this. Like so. Okay. And before we actually carry on, what we should expect at the very end, okay, would be a to the k plus 1 here, which would give us 2 to the k plus 2. So then, if you sub n equals k plus 1, that'd be 2k plus 2, add the 1, that'd be 2k plus 3. That'd be k plus 1 minus 4 times k plus 1, so that'd be minus 4k minus 4, and then minus 2n plus 1. So if n is k plus 1, that's minus 2k minus 2, then add 1, so minus 2k minus 1. Okay, so I think that's right so far. That should be pretty basic. I don't know why that's so difficult, but there we go. So, like any proof by induction, we let n equal 1. So, let n equal 1. So I just get this left-hand matrix here. So is that equal to this? 2 times 1 is 2, plus the 1, that's 3. That's 1 minus 4. And then minus 2 plus 1 is minus 1. Perfect. So left-hand side equal to right-hand side. So therefore it's true for n equals 1. Okay, so that's a good start. Now we just need to assume that it's true for n equals k. So if I do that up here, so assume true for n equals k. So therefore, what we're saying here is that 3, 1, minus 4, minus 1 to the power of k is equal to 2 to the k plus 1, k, minus 4k, and minus 2k plus 1. Okay. Helps if I close the bracket. There we go. So at this stage here now we let n equal k plus 1. So let n equal k plus 1. So we can rewrite this matrix here now, but in terms of k plus 1. So it's 3, 1, minus 4, minus 1, power of k plus 1. This is equal now. So just again splitting this up by powers. So this is 3, 1, minus 4, minus 1. So that's the power of k times by this matrix again, but to the power of 1 this time. So it should all hopefully be pretty standard, straightforward. It's the power of 1. This matrix here to the power of k, we know that that's equal to this. So I can rewrite this. Minus 4k. That's k, and that's minus 2k plus 1. Timing it by this matrix now. And then at this stage here, we just need to do our multiplication. So this one it's a little bit trickier than the last one, but again, nothing too crazy. 2k plus 1 times 3. So if we write this out in full, so this is 3 lots of 2k plus 1. And then minus k times, well, minus 4 times k, we get minus 4k there. Okay, that's just the top left one. Now I do this row again by this column to get the top right one. So that's going to be 2k plus 1 plus k there. Has something gone wrong? I've missed a sign out somewhere. Where have I missed the sign? Ah, that's why. That should be minus 1. I was going to say this isn't going to work. Yeah, okay. So that's minus k. Okay, good stuff. Then this row here by this column, so minus 4k times 3, that's minus 12k. And then minus 2k plus 1, so minus 4 lots of that. Like so. And then finally, the bottom right one, so minus 4k times 1, so that's minus 4k. Minus 1 lot of that, so minus 1 lot of minus 2k plus 1. So now we just need to simplify everything here. So 3 times 2k, 6k, minus the 4k, so that's 2k. That's 2k. 3 times 1 is 3, so we just get left with 2k plus 3. Okay, so that's that one done. 2k plus 1 minus k, that just gives us k plus 1. And again, we get what we needed there. Minus 12k. So that's just what it is. Minus 4 times minus 2k. So that's plus 8k. So minus 12k plus 8k gives us minus 4k. That's good. And then minus 4 times positive 1 gives us minus 4 there. And again, we get what we needed. And then finally, hopefully we get this one right as well. So minus 4k. Minus 1 times minus 2k, so that's plus 2k. So if you've got minus 4k, you add 2k. We have minus 2k left over. And then finally, minus 1 times positive 1 just gives us minus 1 there. And there we have it. Okay, so that's the end of the proof there. At this stage now, you need to write your big waffly paragraph. I'm not going to do it again because it's literally just the same as the last one. But make sure you always finish a proof by induction with that finishing conclusion there. And that's in this video. So I know it's quite a brief one. I feel like these questions are all pretty much the same. If you can do one, you can do them all for the most part. But hopefully that's helped. If you notice any mistakes I've made somewhere, I probably have. Please just let me know in the comments. But yeah, cheers for watching, guys.